Hey guys, welcome to the first video on syn and anti-addition. This is just going to be a video series on these two types of alkene additions, as well as we're going to run through some examples and stuff like that. Alright, so let's just get into it. So what do these terms syn and anti mean? Right, so they refer to types of alkene additions, and you guys have learned alkene additions for exam 1, right? And so what this is now is, because you learned stereochemistry, alkene additions actually, they get a little bit more complicated. There's a little bit more to them. Okay, so syn addition is when the groups that you're adding to your double bond are going to be added to the same side of the molecule, right? So what that means is those two groups are going to be all wedged or all dashed. All right, so all wedged or all dashed. There is no mixture of one wedged, one dashed. All right. Anti-addition is that mixture. One of the groups you're adding will be wedged, and then one will be dashed. Okay. And of the alkene reactions you guys have learned, some of them are syn addition, some of them are anti-addition, some of them don't fall into any of those two categories. Okay, and obviously we'll go through that. So it's easiest to illustrate what I'm talking about with an example. And so I'm going to start out with one reaction. Remember that you guys already know, H2 PDC. So this is a syn addition. All right. Now you're not required to know the mechanism for H2 addition, but it is a concerted mechanism, and it is going to be syn addition. All right, and so that's definitely something to remember or put on your index card. Okay, and so how does this work? So I'm going to draw this structure here. It's alkene, and we're going to try to draw the product. Okay, so when you were learning, when you're studying for exam 1, the answer to this would have just been like this. You would have just left it like that. But now that we know stereochemistry, it gets a little bit more complicated than that. So remember, the definition of syn addition is that the groups that you're adding, in this case, we're adding hydrogens, right? Because remember, there is already one hydrogen right there. We're going to add a second one to that carbon, along with a hydrogen to that carbon. So two groups, right? And so the two groups that we are adding are going to be the same stereochemistry, regardless of whether it is going to be all of them dashed or all of them wedged. They still must be the same. All right. So let's draw the first one. Let's draw what happens if we add the hydrogens wedged. So I'm going to draw that first. All right. So an H, and we have the H. All right. What about that methyl now? So you can see that methyl, because it was part of a double bond, is planar. But when we added those hydrogens, we removed that double bond, and now it is no longer planar. So because the hydrogen at the carbon with the methyl is wedged, the only other configuration that methyl can be is now dashed. It can't be wedged, because remember, if you remember what an sp or a tetrahedral carbon looks like, it's going to look something like this, right? Two planar bonds, a wedge bond, and then a dashed bond, right? So we already have the two planar bonds right there and right there, and we have the wedged one right there, so we have to make the methyl dashed. So the methyl is going to be dashed, right? And remember, this hydrogen here that was also planar, because we added a wedged hydrogen, that is also now going to be dashed. Okay? So that's the product if the hydrogens are all wedged. What about if they're all dashed? Right? That's another possibility. there is no preference for whether it's going to be add wedged or dashed. That's why we have to draw both. So that is only one of the possible products. We can also have another one. So if you want to pause here and try to draw a dash, please feel free to do so. So how is this going to look? It's going to look now like this. Now, because that hydrogen with on the carbon with the methyl is dashed, the methyl is now going to be wedged. That's going to be there. And the hydrogen, that red hydrogen that used to be planar, because the blue hydrogen added is dashed, it's going to be wedged. And so we get those two products, okay? And so you can see that we have two products, and what I want to point out for you guys is this carbon and this carbon. You can see that it has 4 unique substituents, so it's chiral. It's also the only chiral carbon on that molecule. If we do the RNS configuration for it, you will see, and actually let's just do that right now. So let me just remove that. So let's remember our priority, right? What's going to take priority is going to be this chain as number 1, number 2, 3, 4. Cross out our group 4. Draw your arc from 1 to 2 to 3. It looks clockwise, which would be R, but because our lowest priority group is wedged, we reverse that. So that's going to be S. Let me just erase this for more room. And let's do the same thing here. This is going to take the higher priority. Second, third, fourth, cross out 4 and draw your arc from 1 to 2 to 3. That's clockwise, which looks like it would be R. And in this case, our lowest priority group is dashed, which is the easiest case, and we leave it as R. And so what did we get here? We got 2 enantiomers, right? We have a mixture. In one group, we added them wedged. In the other, we added them dashed. And so you have to realize, you have to be careful here and understand that we produced 2 enantiomers, right? Because the only chiral carbons on those molecules are the exact opposite in terms of RNS configuration on the 2. So that's 2 enantiomers. And so when we form a mixture of 2 enantiomers like this, and remember, there is no preference for if it's going to add wedged or dashed. So essentially it's 50-50. When you get this sort of mixture, it's called a, let me write it here, racemic mixture. You must understand this term. When you have an equal mixture of enantiomers, remember, enantiomers have something called optical activity, which means that they can rotate the plane of light, I guess. Okay. Racemic mixtures, because it's composed of 2 enantiomers, even though the enantiomers themselves are optically active, because they're in an equal mixture of each other, there is no optical activity. Okay, so please know those definitions for the test. They could 100% come up. All right, so let's try another example of syn addition using the same H2PDC. So we have this molecule. Okay, and so now let's again change the color of those hydrogens. So let's draw the product. Okay, so we could draw them all wedged. And so how would that look? It would look like this. H, H, and because the hydrogens are added wedged, the methyls will now be dashed. Okay. What about if we added them dashed? Just move this over. So now we can add them dashed. And our methyls will now be wedged. So, did we get two products here? It may look like we've gotten two products, but remember, if you look, we have two chiral carbons on each of them. One right there, one right there. Right, same for this. The problem is, if we look at this molecule, I can draw this line down the middle, and you can see that we have a plane of symmetry on each of them. So what does this mean? These are meso compounds. And remember, the thing about meso compounds is that these two are the same compound. The only difference between them is I flipped one 180 degrees. So if I take any of them, flip it 180 degrees, it will perfectly overlap with the other. So they're the same. So in this case, you get one product. Okay? And it's one achiral product. Remember, a meso compound, despite the fact that it has chiral carbons, is considered an achiral compound. So you get a single achiral compound. Now let's look at an example of anti-addition. Okay? So I'm going to draw this. And so what is an anti-addition? What reactions qualify as anti-additions? Well, any of the reactions with the halogens that form a three-membered ring intermediate, those are considered anti-addition. Okay? Not the ones that form carbocations. In fact, carbocation forming reactions do not fall under the category of syn or anti-addition. All right, so be very careful about that and understand that carbocations are not syn or anti-addition. It's completely different. So any of the halogen reactions that can form the three-membered ring intermediate, those are anti-additions. So I'm just going to start out with Br2, keeping it simple. All right, and so let's try to draw our product. Now again, prior to what you guys are learning now, when you were studying for exam 1, you would have written the answers like this, right? Two BRs adding across the double bond. But because of stereochemistry, it's going to be a little bit different. All right. So what happens is that one of the BRs will add wedged. The other one will add dashed. And why does this happen? Well, it's because of the mechanism. And so I'm going to actually go through this mechanism because it's very important that you guys understand this. Okay? So remember how this works. The double bond attacks the Br. This bond breaks. And this Br attacks the carbon of the double bond right there. So what we're going to get now is we're going to get a ring intermediate, right? So it's going to look like this. So, on the plus charge, okay? So you can see that the two bonds to the Br and the carbons are the same stereochemistry, both wedged. That's a very important thing to understand. They're both wedged. But we could have very easily have had the other reaction, the other stereochemistry, where we get the bonds as dashed. Right? It's again, there is no preference, so it's 50-50. Okay? So we get this happening here. And so now what ends up happening? Remember that we have, again, the other Br minus still floating around in both cases, assuming these are almost like separate, taking place separately. And it's going to attack the more substituted carbon. Now, the thing here is that it's going to attack the back of this molecule, right? So the wedge is coming at you, right? The wedge bonds means they're coming at you. And so what the Br minus is going to do, it's going to perform a backside attack at this carbon. So it's coming in from the back. It attacks there and kicks this out. Okay? And so it does the same over here. It's going to come in right there. kicks that out. And so what's going to form now is this. The Br that was originally added retains its stereochemistry. So the one that is going to get kicked off kind of is going to be now staying as wedged. The one that attacked second is going to be the opposite stereochemistry. So it's going to be now dashed. And the methyl now is wedged. Let me draw that better. And in the other scenario, this one is now going to form dashed. Remember, the Br part of that 30-member ring intermediate that will be on the least substituted carbon retains the stereochemistry. Now this Br, that second one that added, is going to add wedged. And the methyl is going to be dashed. Okay? And so you can see that the Brs are not the same stereochemistry like we had here, where the hydrogens were either all wedged or all dashed. In this case, they're the opposite. One is going to be wedged, one is going to be dashed. All right? And so if you also look at here, these are also enantiomers, right? They're going to have unique substituents on all of them, on 2 of the carbons. Look, this one is going to is a chiral carbon, and so is this one. All right, and same thing here. So you could do the RNS configurations, and you'll see that they're also enantiomers. And so in this case, we again generated something called a racemic mixture. Okay, and so yeah, so that is also that's an example of an anti-addition. Now remember, I could have just as easily put a solvent here, ROH, and in this case, instead of the Br attacking second, the ROH group attacks, and we'll get an ether group, this OR group, instead of the second Br that attached, which was that one, or that one, or it could have again been OH. All right, and so those are examples of syn and anti additions. In the next video, I'm going to be going over I'm going to show you guys all the reactions that are syn and anti, and we can go through some examples and stuff like that. And the videos after that, I'm going to show you guys some common things that trip people up, mainly with H2PDC. It's due to bond rotations, all right? And so if something in this video didn't make sense, please feel free to email me or talk to a TA. They will be happy to help you guys. If you're watching this on YouTube, please feel free to comment below so that others with the same question can also see it, and they'll see the answer. And when I answer it, they can also get their answer as well. All right? And so I will see you guys in the next video. Good luck.